This is the last mini lecture in the Transonic aerodynamics, and it's about the designs to conquer the sound barrier. And because in the previous lectures we already noticed when the aircraft approaches to Mach 1, so the drag coefficient of the aircraft will increase significantly. And in here we will discuss the design methodologies to address the significant increase of the drag coefficient. So sound barrier, we've already briefly seen what is the sound barrier. Now let's revisit the material, and we've seen this curve CD versus free stream Mach number, and we already know at the critical Mach number, the sonic region starts to build up over the aerofoil, but it's very small region called a supersonic bubble. But once it's beyond the critical Mach number and close to the drag divergence Mach number, the supersonic region will become sufficiently large and make the drag to diverge, in this case, to increase significantly beyond point E. So regarding sound barrier, we are talking about the region in EFG along that part of the curve. So in that region, the CD will increase by a factor of 10. So it's a so significant increase, so big increase, and it's like a barrier for the aircraft to overcome. So that's why we call it sound barrier. And actually, we've already seen what happens in the flow. Just use a sketch to remind you what happens. So in the region EFG, we are expecting the second and the third flow pattern. So the second flow pattern has I would say reasonable size of the supersonic flow, and the shock already is quite strong, and we see there's possible flow separation after shockwave. But once the free stream Mach number increases, in this case to 0.82, we can see the normal shockwave over the top surface is even stronger, and there's considerable flow separation over the top surface. Moreover, over the lower surface, there's a shockwave appearing. So in this case, it will produce even larger drag for the aircraft or for the wing. So this is a definition of the sound barrier. Okay, so now we will see what our aerodynamic designers to address the sound barrier, to address the drag increase. So the first design is the swept wing. We are quite familiar with that. Nowadays, all the transport aircrafts are equipped with the swept wing. And I believe in the other modules, you must be familiar with the reason. And some people explain as using the swept wing, we can decompose or project the free stream velocity vector, and then because the swept angle, the actual or effective velocity the wing leading edge experiences is smaller than the free stream velocity. So this is one possible explanation. Now we see another explanation. So you can see here in the plot, we have a straight wing and a swept wing. So the straight wing has a chord of C1, and the thickness is T1. The maximum thickness is T1, and we have 45 degrees swept wing in order to make the wing area the same, right? So we can maintain the length of the leading edge the same, and simultaneously the height of the parallelogram should be C1 2. So it's indicated through the red dotted line C1. So and in this case, the straight wing and the swept wing will have the same area. But the other chord C2, which is a chord along the fuselage or streamwise direction, C2 is 1.41 times of C1 because it's 45 degree, and C2 is equals square root 2 times C1, so it's longer. So C2 is longer than C1. And now, since the maximum thickness T2 is actually the same as T1, we are not changing the airfoil, just elongate it. So what we can say is a ratio of thickness with respect to C1 and becomes smaller for the swept wing because the denominator becomes larger. Then the swept wing effectively has a thinner airfoil compared to the straight wing. Is that right? So we already know from the earlier lecture that a thinner aerofoil has a larger critical Mach number. So this helps to alleviate the drag increase for the transonic flight. So showing here is I think a World War II aircraft. So it has equipped with a swept wing to address the drag increase issue. Okay, so for swept wing, we take this is for the swept wing. The second design is area ruling. Perhaps this is not so familiar to us. And let's see what's area about. What's area? Since the title is about area ruling. And where's the area? Okay. So before we introduce the area ruling, we can see the evolution of aircraft design. And the left one is North America F86, and the right one is from the same manufacturer, F106. Apart from the wing, if we focus on the fuselage, can we spot the differences? I give you 1 second. Right. So the fuselage for the left one is quite straight, but for the second one, you can see there is a bit narrowing. One's in the middle and then expand slightly. So that's a difference. Okay, so if we take a look at the cross-sectional area of the aircraft, which means we are cutting, for example, we have the top view in here, we are cutting the vertical cut, and so we get a lot of slices. It's like the loaf of the bread, right? Okay, so we can see some indications in here. So in the sketch below, we can it's just a conceptual drawing. The left is a straight fuselage. The right one is like wedge-shaped fuselage, similar as F106. And we can see the cross-sectional area distribution. The right distribution with the neckline of the fuselage, we can see the distribution becomes smoother than the straight fuselage. So this is a so-called area ruling, and the area ruling is to maintain the smooth transition of the cross-sectional area distribution, and this is by experimental evidence enables reduction of aircraft drag. So this is a design concluded from the experiments or wind tunnel experiments, and we can see some other examples. For example, the F102, and you can see the left one, black and white picture, is the original design of the F102, and the right hand side one, the color one, is updated design. So you can see the difference of the fuselage. The original one, left one, has no area ruling, but the right one has the area ruling. And we can see some sketches. This is from the Anderson book, and we can find the F102A with area ruling provides a smoother transition of the cross-sectional area distribution along the longitudinal axis. And if we do the measurement, although it's a conceptual sketch, again here we expect the CD have less increase at the critical Mach number, or drag divergence Mach number. So this is what we expect. Okay, now we can finish the second design, area ruling. So the last one is called supercritical aerofoil, and it's used in every transonic aeroplane nowadays, I would say. So a supercritical aerofoil is an aerofoil designed primarily to increase the drag divergence Mach number and to delay the onset of wave drag in the transonic speed range. And so here is a one-to-one comparison of the conventional aerofoil and the supercritical aerofoil. So for the supercritical aerofoil, let's see the features. It has increased nose radius, and the top surface is flatter, so flat upper surface. And since we want to generate lift, we need to introduce some camber to the aerofoil, so the camber is concentrated close to the trailing edge. And also we have blunt trailing edge. So this is the design features of the modern supercritical aerofoil. And so you may wonder, is there a difference of the flow field? Yes, there are. And if the shock appears, we expect normal shock wave, strong normal shock wave on the conventional aerofoil, but the supercritical one, we expect a weaker normal shock wave, and also it's more downstream. And since the shock wave is weaker on the supercritical aerofoil, if we look at the pressure distribution at lower, and we can find that pressure increase is smaller over the supercritical aerofoil. So, and this is what we have for the three designs to address some barrier. Hope you can understand all the design features and their underlying mechanisms. And finally, I would like you to remember these two people. So you may say, and there are three designs, only two people. Why? Because one person, Richard Wickham, has the credits for the area ruling, and both the area ruling and the supercritical aerofoil. So he's really important in forming the modern transport or transonic transport aircraft. So Adolf Bussmann is proposed the idea of swept wing, and he was originally a German, and after World War II he moved to the NASA Langley Center and continued his research in the swept wing aerodynamics. And Richard Wickham is also an aerodynamicist in NASA Langley Center. They are actually colleagues, and Richard is about 20 years younger than Bussmann, so they do have communications during their in NASA. Okay, so till now we've finished the transonic aerodynamics, and we covered most of the important parts of transonic aerodynamics.